So I will be talking today about carbohydrates. So carbohydrates, what do you mean by carbohydrates? Carbohydrates, as the name suggests, they are hydrates of carbon, and the basic formula, it stems from CH2O N. This is carbohydrates, where N will be greater than equal to 3. In the biological system, carbohydrates are synthesized through the process of photosynthesis and gluconeogenesis. As you know, photosynthesis occurs in plants and gluconeogenesis both plants as well as in, especially it is important in animals. Carbohydrates can be divided into one side you have the monosaccharides, you have the disaccharides, you have the oligosaccharides, and you have the polysaccharides. The word saccharide comes from the Sanskrit word shakkar, which means sugar. So it's a sweet story, you can say. So monosaccharides are where you have one sugar molecule, glucose, fructose. Example: glucose, fructose, galactose, all these things you have heard. And the disaccharides are the famous, where you have two sugar units, two sugar molecules attached together. Example: sucrose is the most famous one. You have lactose, galactose, maltose. Then oligosaccharides, they roughly say they are 2 to 10 sugar molecules. Raffinose is one example. RAFFINOSE, raffinose. You have raffinose or stachyose. And then you have the famous polysaccharides, where 10 or more sugar units are present. Example, you know, starch, glycogen, cellulose. Starch and glycogens, they are also known as storage polysaccharides. And cellulose or chitin, they are structural polysaccharides. Now let us consider about monosaccharides in details. So monosaccharides are basically, they are simple sugars. They are aldehyde or ketone derivatives, of straight chain polyhydroxy alcohol. So essentially, let me draw the structure of the most famous monosaccharide of them, glucose. You have an aldehyde group, six carbon, 1, 2, 3, 4, 5. You have CH2OH here, COH, so basically this is the structure of glucose, and this is carbon 1, 2, 3, 4, 5, 6. This is the 6th carbon. So this is also known as a Fischer projection. Now glucose, they can be classified into by the DL system of classification. It can be D-glucose or L-glucose. The most simplest carbohydrate is glyceraldehyde. Now if you look at a glyceraldehyde molecule, you have 3 carbon, this is CH2OH, and make this correction over here. So this is known as D-glyceraldehyde. Now you can see that this is carbon 1, 2 and 3. If you look at carbon 1, 2 and 3, which is the chiral carbon then? A chiral carbon is the carbon which is attached to 4 different groups. If you see at the first carbon, it is not attached to 4 different groups. One group is this group over here, second group is only the O, and the third group is H. So it is not attached to 4 different groups, so it is not the chiral carbon. The carbon number 3, if you see, it is attached to 2 hydrogens, so it is attached to 2 same groups, so it is still not the chiral carbon. Only the second carbon which is attached, this is one group, this is another group, this is the third group, and this is the fourth group. So the chiral carbon is carbon, this is the chiral carbon. And now if the oxygen hydroxyl group and the oxygen is on the right hand side, this is the D configuration, and it is known as D-glyceraldehyde. And if it is on the, this OH is on the left side, this is the L configuration. This is L-glyceraldehyde. So these are isomirror images of each other, L and D. Similarly, if you look at the case of glucose from this condition, glucose has got 1, 2, 6 carbon, 3, 4, 1, 2, 3, 4, 5, 6. They have got 6 carbon. CH2OH. Okay. Now if we look in the case of glyceraldehyde, which is, what do you say, what would you consider to be the chiral carbon? What are the chiral carbons? So let us draw L and D glyceraldehyde. First let us draw the D glyceraldehyde. So 1, 2, third carbon, fourth carbon, fifth carbon, and sixth carbon. Now let us draw the groups. In the third carbon, the OH is on the, in glucose, it's on the left. The others fall on the right. So here this is the structure of L-glucose. Now the chiral carbon which is farthest away. So this is a chiral carbon, this is a chiral carbon, this is a chiral carbon, this is a chiral carbon. So you have these 4 chiral carbons over here. They are attached to 4 different groups. So the chiral carbon which is farthest away, the chiral carbon which is farthest away from the first carbonyl carbon. Where is the OH located over there? The OH is located on the right side, and therefore this is D-glucose, not L-glucose. So this is how other carbohydrates are compared. The chiral carbon which is on the furthest carbon from the carbonyl group, that is, the OH is on the right hand side, and so it is D-glucose. Similarly, here this is going to be a mirror image. The OH comes over here. The OH was here, it comes over. I'm drawing it the other way around, so let's wipe it. So here H, OH, OH, you are drawing a mirror image of each other. And this is L-glucose, because the chiral carbon 1, 2, 3, 4, 5, which is furthest, it has got OH on the left side, so it is L-glucose. So in nature, D sugar configuration is the most common occurrence. D sugar configuration is the most common occurrence. With this, we go up to the next part. Next path is the Fischer to Haworth projection. So these linear configurations which we saw over here, this type of straight chain, this is the Fischer configuration. This can be made into a cyclic configuration, and that is the Haworth projection. So this actually, the alcohols, they react with the carbonyl groups of aldehyde and ketones to form hemiacetyl or hemiketal respectively. So the reaction occurs like this. This is R group, it has and an OH group. This is the alcohol group. If you add with R dash, this is the carbonyl group CHO. What happens is, in this reaction, it forms R O this compound which is formed, this is known as the hemiacetyl. So here you have two molecules reacting, first molecule and second molecule. This R goes over here, this H goes off, and this double bond breaks here. So when this particular reaction, here you see two molecules happen. When it happens in the same molecule, for example, let us draw glucose. This is the carbonyl aldehyde group. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. This is a CH2OH group. It's, you draw it like this. So this is D-glucose, which you are drawing in a Fischer projection. D-glucose Fischer projection. Now what happens when this OH attacks here? It's the same molecule which takes place. A cyclization takes place, and what you find eventually is HOH. This is the other way around. Oh, this we forget. You have a structure which is similar, something like this. Let us mark the carbons over here in red or green. So if this is 1, 2, 3, 4, 5, 6. So this is 6, 5, 4, 3, 2, 1. Now two things can happen. This is the first situation which can happen. And the next situation where this OH is on top. The second situation which can happen is see this OH is on the bottom. OH on the bottom. So this configuration is known as beta glucose, and this is alpha glucose. So this type of a ring is known as a pyrene ring. So a pyrene ring has got a structure something like this. This is a pyrene ring. Happens when alcohols attack, but when ketones attack, ketone cyclize, as in the case of fructose, you have a structure something like this. This is a furan, and so this glucose is also known as beta D glucopyranose, and this structure is also known as alpha D glucopyranose. And this carbon over here, it is also known as hemiacetyl carbon or anomeric carbon. So the first carbon is hemiacetyl carbon or anomeric carbon. The next concept which we will be studying is mutarotation. Now what is mutarotation? There is this change from alpha D. Whenever glucose is in solution, there is a change from alpha to beta. It keeps on going simultaneously. So if we draw alpha glucose, the OH is below, OH is above, OH is below. This is alpha glucose. This breaks down in solution. And forms a straight chain. This again cyclizes and it forms beta glucose. This is beta glucose which has formed. This keeps on happening from alpha to straight chain to beta glucose. This keeps on happening. And if you see the optical rotation values, if you in a plain light, if you pass light through this, there is a rotation happens in the molecule. The optical rotation of alpha glucose are plus 112.2 degrees, and for beta glucose it is plus 18.7. And when this keeps on happening, degrees, not centigrade, degrees, angle, keeps on shifting from here. So the average optical rotation which you find when the equilibrium is reached, where equal number of alpha glucose gets converted into beta glucose and equal amount of beta glucose gets converted to alpha glucose, that is 52.7 degrees. So this phenomenon is known as mutarotation. The next thing which we will study is tautomerization. 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 Now what is this tautomerization? Let us draw glucose in a special manner. I am drawing the CHO group like this. OH on the left, on the right. One, two, three, four, five, six. This is D glucose. Have a look at this group over here. Beside it, I am drawing the structure of fructose. CH2 OH CO, and the rest is similar to that of glucose. This was D-glucose. Now we have D-fructose. Beside it, I am drawing another structure, that is D-mannose. Here it was on the right, now I am drawing this on the left. So the rest is same as that of glucose. This is mannose's structure. This is the structure of mannose. In alkalic solution, what happens when glucose is placed? In alkali solution, when glucose is placed, a strange thing happens. This double bond migrates over here, and an intermediate known as COH, this double bond here, it migrates over here. A resonance takes place, and this structure forms. From this you can have a fructose being formed or a mannose being formed, because this breaks up, this opens up, and when this rejoins, if this double bond migrates over here, it will form this fructose. If it migrates back and this OH goes on this direction, it forms mannose. So this process of shifting a hydrogen atom from one carbon to another, and this structure, this is known as enediol intermediate. In glycolysis you will find this sort of intermediate a lot, this enediol intermediate, and so this is known as tautomerization. So these are enediols. Okay, next part we go is what is glycosidic. What are glycosidic bonds? So glycosidic bond or glycosidic linkage, it is a type of covalent bond that joins carbohydrate molecule, one molecule of carbohydrate with another, that is glycosidic bonds. So let us see what is a glycosidic bond, what happens in a glycosidic bond. Let's draw two sugar molecules. Now I am drawing it in a very I am not drawing the hydrogen. The OH is below. This is the C1. You have the OH below here. CH2OH. I am only drawing the OH, I am not drawing the H over here. And neighboring this is C1, C2, C3, C4, C5, and on the top C6. Let's draw the next one beside it. Another, say this is alpha glucose. I draw one more beside it. So you have two molecules over here next way. Now this, a molecule of water is removed, and this is a condensation takes place. Water is removed, and what is formed over here is so this bond which is formed over here, since this was alpha glucose, this was also alpha glucose. This was carbon number 4, 1 to 4. So this is a alpha 1 to 4 glycosidic linkage. So a glycosidic bond is formed over here. So this is all about. Now you find when this is formed, this is the molecule which is formed over here. This is a disaccharide known as maltose. Two alpha glucoses joined together. Similarly, other disaccharides which are formed, this is also known as O-glycosidic bonds, because there is an O there. This is a O-glycosidic bond over here. Now let's have a look at how a famous disaccharide known as sugar looks like. Sucrose, the common sugar. This is common sugar. The OH is on the top, H below, H, OH. This is let's draw it with a different color. This is 1, 2, 3, 4, 5 and 6. Similarly, this is 1, 2, 3, 4, 5. This is 6. The third is the other way around in glucose. So this is an alpha, and this is in ketone, this is a beta. So this is a glycosidic bond in sucrose. Similarly, you have to study the structure of lactose and maltose. Lactose is glucose plus galactose, where you have a glycosidic linkage formed. Now let us migrate to the next part, which is polysaccharides. As you know, they are divided into structural polysaccharides, famous among them are cellulose and chitin. Let's have a look at the structure of cellulose. First, always draw this. CH2OH. Here the OH is on the top. So the linkage is like this. It's not from the bottom, because these are units of beta glucose. Remove the H from here. Like this, if you have n number of units, you form cellulose. So from S. Satyanarayan's book, I would suggest you to read about the structures of chitin and cellulose. Now let us go to the first storage polysaccharide. The first storage polysaccharide is what we need to study is starch. and the second is glycogen. So I will give a brief short break over here. In the next video we will continue this part.